大家好. Hello, everyone. Welcome to Layers of Isolation in Kubernetes. My name is Tim Allclair. I'm a software engineer working on Google Kubernetes Engine. I'm also a co-chair of Kubernetes SIG Auth and a member of the product security team. So today I'm going to tell you about isolation in Kubernetes. But before we start with that, let's make sure we're all on the same page for what isolation means. A model of isolation and security that I really like is the CIA model. This stands for confidentiality, integrity, and availability. Confidentiality means that an isolated process cannot read information or state or data from outside of its isolation boundary. Integrity means that the isolated process cannot alter the state or the data of things outside of its isolation boundary. And availability means that the isolated process cannot compromise the ability of things outside of its isolation boundary to do their job, affecting services and whatnot. And before we go on, there's two key properties of isolation I want to point out. The first is that this is really a multi-dimensional problem. It's not enough to, for instance, isolate just the CPU and memory resources to prevent denial of service, compromising availability type attacks. There's a lot of other ways that you can cause a denial of service. And so to have a secure isolation boundary, this really requires a holistic approach because attackers will find the weakest link. The other property I want to mention is that this is a directional thing. As an example, a process in a container has a good isolation boundary around it, and it's not able to access things on the node. On the other hand, a root process on the node can easily access any data that's running in that container. So we see that there's this sort of directionality to isolation. So these are the 6 layers I'm going to talk about today. And along with the theme of directionality, we see that the first 4 layers are within the cluster. So we're talking about something that's already running in the cluster and what is isolated within the cluster from that. So why might you care about this? The first reason is defense in depth. If you have a service that's exposed externally, maybe there's a remote code vulnerability, remote code execution vulnerability in that service. And an attacker manages to get access to running within your container. If you have good isolation, then you can prevent that attacker from being able to further escalate privileges and access data within the cluster that they shouldn't have access to. The second reason you might care about this is if you're running any sort of multi-tenant environment, maybe you're a SaaS provider, and you have different customers running on your cluster, and you don't want them to be able to affect each other. You want good isolation between those customers. So let's start with containers. How much isolation is there between 2 containers running in the same pod? There's actually quite a bit. Docker has done a lot of good work on coming up with good security defaults. And, so they've done a lot of work. We've adopted those in Kubernetes. And short of known vulnerabilities, it's very hard to escalate privileges out of a container if you're using best practices. So what are some of those features that enable container isolation? In Kubernetes, we isolate CPU and memory resources, and disk as well, by setting requests and limits on containers. CPU and memory is enforced by the kernel through C groups, setting limits that, on what the container can use. And disk is sort of a softer enforcement that's done by the kubelet. Kernel resources are isolated through things like namespaces. So for instance, containers run in separate mount namespaces, have separate file systems, and this means that one container writing a file to its root file system, that file isn't going to be accessible in the other container, unless, of course, you're writing it to a shared volume. Similarly with process IDs, they can't read each other's processes. And there's a number of other kernel security features that we enable to reduce the attack surface and prevent known privilege escalations. Capabilities is a sort of coarse-grained permissions in the Linux kernel that let us prevent certain classes of syscalls. Linux security modules such as AppArmor and SELinux can further scope down what a process is able to do. And on AppArmor-enabled nodes, we enable the Docker default AppArmor profile, which prevents access to sysfs and other pseudo file systems that can be used maliciously. And then we have some best practices too. You can enable seccomp through an annotation on the pod. And this will further reduce the number of the syscalls that the container is able to make, blocking some dangerous syscalls. But of course, the best thing that you can do is to just run as non-root. If you're able to do so, this is by far the best security guarantee you have in a container. So what isn't isolated at the container level? First of all, we haven't done anything with network. We'll get to that in a minute when we talk about pods. While we've isolated some hardware resources, this isn't a perfect sandbox. And there's still some things like disk contention or IOPS and bandwidth that aren't fully accounted for at the container level. This is something that we're constantly working to improve, and so you can look forward to improvements in the coming years in these areas, but we're not quite up to par with VM level isolation here. Another one is kernel resource exhaustion. Although we have a PID namespace, it's still possible to run out of process IDs through things like fork bombs. We'll see an example of that in a second. And lastly, identity is typically bound to pods. It is possible to have separate identities per container, but it's not typically done. So let's look at an example of how a container can compromise the availability of a node. I'm going to run just run a simple Alpine container to get access to my cluster. And let's take a look at the uptime. So already here we see a compromise of confidentiality. This isn't particularly sensitive data, but this is an example of some data about the node that is accessible to within the container. This is the uptime of the node, not the uptime of the container. So let's go ahead and shut down that node. Fortunately, this operation is not permitted by default. This is because it requires the system boot capability that's dropped by default in Docker. There's actually a few other mechanisms as well that prevent us from doing this. But we have other tools in our toolbox. Remember, security requires a holistic approach. So this you might recognize as a fork bomb. This will spawn a process that continuously spawns 2 copies of itself. In doing so, it'll eventually exhaust the PIDs that are available, so new processes can't be run. It'll cause CPU contention and eventually eat up a lot of memory on the system as well. And some of these things aren't fully accounted for with the C groups, so even setting CPU and limits won't help you. Fortunately, as of Kubernetes 1.10, we have an alpha feature called Support Pod PIDs Limit. If you enable this feature, you can then set a maximum process IDs that a pod is allowed to use. This is an example of pod level isolation, and doing so will prevent fork bomb type attacks. So with that, let's move on to pods. How much isolation is there between 2 pods in the same namespace on the same node? Well, first of all, processes aren't really running in pods, they're running in containers. So we get all of the isolation that we already talked about with containers, and then we're going to layer on a bit more. First of all, we finally get network isolation. So we have a separate network namespace at the pod, and that comes with a virtual Ethernet device that's associated with that pod, its own IP address, and this lets us apply network policy as well for good network isolation. We'll see an example in a minute of why network policy is important. Service counts are typically associated with a pod, so we now have the ability to have 2 separate pods with different identities running. And a lot of Kubernetes policies are applied at the pod level. Pod security policy, network policy we just mentioned, and scheduling policy is a work in progress for constraining the way pods are scheduled. And then volumes are another resource to mention that are bound to the pod. Empty dir volumes, for instance, have their life cycle tied to the pod, so when the pod is terminated, the data is deleted. So what isn't isolated at the pod level? Well, as with containers, we haven't really added a lot of hardware or resource isolation. We at least have a separate network namespace, so we have the building blocks to add in bandwidth isolation here, bandwidth limiting, but we haven't implemented that yet. Kernel resource exhaustion is still an issue. We saw how the pod PIDs limit feature can be used to prevent PID exhaustion, but file descriptors is still an issue. And it's important to remember that this is still only a single security boundary. So even though we're talking about a second layer in that initial diagram, we're still relying on the kernel to enforce all of these things for us. That means that a single vulnerability that is exposed despite our attack surface reduction could potentially be used to escape out of a container and out of the pod as well. So let's look at an example of why network policy is valuable. Again, I'm going to run an Alpine container to get access to my cluster network. And I'll go ahead and grab the Nmap utility that lets me scan the network. I could scan every port on every IP address within the private cluster IP range, but this would take a very long time, so let's not do that. Instead, I'll just grab the IP address of the first node. The JSON path is just a trick to grab the IP address I'm looking for. You could also do it manually. And I can do a similar thing to get the pod CIDR range, so all of the IP addresses that could be used for pods. Now that I have those, I can scan just the node IP address, and we see that this is a Kubernetes master node. Taking a closer look at some of those ports, as it's a master, we see the Kubernetes API port is there. We also see that etcd is actually exposed on the internal network. Now, fortunately, in this cluster, this is an authenticated etcd endpoint, and so I don't actually have access to it, but it's important to make sure that etcd is in fact authenticated on your network, because having access to etcd is equivalent to having root access in the cluster. Now let's jump forward to port 10255. This is the kubelets unauthenticated read-only port. It's read-only, so I can't do too much with it, but I can get some interesting metadata about workloads running in the cluster. Let's take a closer look at that. There's a pods endpoint that's exposed, and if I look at that endpoint, I actually get a list of every pod spec running on that node. I can query every node in the cluster, and now I know every workload that's running in the cluster. It is possible to turn off this endpoint, but it's a little tricky, as a lot of monitoring tools rely on the metrics that are exposed through the read-only port. But that's something we're working to improve. Just one other example. Here's the Kubernetes dashboard, and we can switch over to the browser view. Fortunately, the modern Kubernetes dashboard uses authentication and authorization to make sure that without proper credentials, I can't do anything too harmful to the cluster. That wasn't always the case, and there have been a few high-profile breaches caused by dashboards that were exposed publicly by accident. So make sure you're running an up-to-date dashboard and have proper controls on that. So all of these things could be blocked with a good network policy. For instance, if I have a workload that doesn't need to talk to nodes or need access to the dashboard, I can easily block that with network policy, as just a couple examples. So let's move on to talking about Kubernetes namespaces. This is different from the Linux namespaces we talked about at the container level. So with namespaces, I get stronger identity isolation. We already mentioned that we can have different identities at the pod level, but by default, all pods in a namespace run with the same service account. With different namespaces, it's actually not possible to run those pods with the same service account. And along with that, I have stronger authorization controls. And we'll look at an example of that in a second. And then lastly, a bunch of Kubernetes resources are bound to namespaces, and having pods in separate namespaces limits their ability to access some of these resources without granting access explicitly through the control plane, through RBAC or something like that. But it's important to note that namespace isolation and Kubernetes namespaces is purely a control plane concept. It doesn't actually have any effect on the node. So once those pods are running and fully set up, there's no additional isolation between them, except at the control plane. So I mentioned that namespaces are sort of a building block, the fundamental building block for authorization. It's actually possible to limit access to specific resources in a namespace through RBAC, but doing so has some nuances that can be problematic. So let's look at why. Here's a user that is forbidden from accessing secrets in the default namespace. However, they do have the ability to create pods. So here's a simple pod spec that mounts a secret volume. Now I have to know already what the name of the secret I'm trying to access is, but we just saw how I can use the pods endpoint on the unauthenticated port of the nodes to see what secrets are mounted by other pods in the network. So I create this pod successfully. I have the permissions. And at this point, there's very many different ways that I can exfiltrate this data out of this pod. Just to keep things simple, I'll assume that I have exec access and can copy the data out. And now I have access to this secret despite being forbidden from accessing secrets. So what can you do about this? It's important to kind of understand the nuances of all the different permissions that you're granting. But to make it a little easier, we have a few built-in roles in Kubernetes, the viewer and the edit role, which when bound at the namespace level will appropriately limit to what is actually granted by that role. So let's move on to talking about nodes now. And we're going to shift gears a bit here. So far, we've been talking about isolating processes running within a container. But now, at the node level, I'm actually going to assume that an attacker has already managed to escape the container. So maybe it was running as a privileged container, and there's a number of ways to get out from there. Or maybe there was a kernel vulnerability they were able to exploit. So let's look at what this attacker that has root on a node is able to do. How much isolation is there between different nodes on the cluster and the control plane? So first of all, we already mentioned that we're assuming the attacker has already escaped a container. So that means we're actually introducing our first second security boundary, or introducing a second security boundary for the first time. That's important because we said that maybe the attacker takes advantage of a kernel vulnerability to escape the container. But now they need an additional vulnerability, hopefully, to escalate through the cluster. So in addition to that, we finally have hardware-level resource isolation, or at least as good as our VM infrastructure that we're running on. So things like disk contention and bandwidth generally are accounted for much better at the node. And what isn't isolated at nodes? Well, we've actually taken a step back in network isolation. At the pod level, we were able to use network policy to firewall off the network from the pod. But network policy applies to pods and not to nodes. We could use firewalls within our infrastructure and set up our network in such a way to firewall off nodes, but this is hard to do because pods tend to move around to different nodes. and so it's generally not done. Additionally, even if we firewalled off the network, nodes have access to a lot of metadata about the cluster. The kubelet can list all pods running in the network, or running in the cluster. And the kubelet needs access to a number of other things like pod credentials and secrets. Also, in addition to the kubelet's resources, we also have access to every credential used by every workload on that node and all of the permissions associated with those credentials. So let's look at an example of that. Here's a simple setup. I have 2 nodes, 2 pods, 2 secrets. To make it easy to remember, pod 1 mounts secret 1 and runs on node 1. Same with pod 2. So let's SSH into node 1 and see what we can do. Using the kubelet config and the kubelet credentials, I can use kubectl as I normally would, but acting as the kubelet identity. So we can see that I can list all pods. And let's take a closer look at pod 1. As I mentioned, it mounts secret 1 and runs on node 1. Because the kubelet needs to be able to access the secret in order to mount that secret into the pod, we can see that the kubelet, in fact, does have access to that secret. Now let's take a look at pod 2. Similarly, pod 2 mounts secret 2, runs on node 2. Remember, I'm still running as node 1. Node 1 doesn't need access to secret 2, assuming there aren't any other pods running on node 1 that mount that secret. So we see that if I try and get secret 2, actually I'm forbidden from doing so. And the reason this works is because of the node authorizer and node restriction plugins. These plugins maintain a graph of all of the resources that are referenced by every workload running on a node and restrict access to the resources that the node doesn't actually need access to. This was introduced in Kubernetes 1.7, and we've been making improvements to it since then, further scoping down what the node can do and ways that it can steer pods to itself in order to gain access to things that those pods need. Now I want to just take a quick aside here and talk about Sandbox Isolation, which is a feature that I've been working on and I'm pretty excited about. The goal of Sandbox Isolation is to bring the second security boundary and a lot of the things we just talked about around node isolation and bring them to the pod level. So in some ways, this is actually even better than node isolation, right? Because we talked about how at the node level, we took a step back in the network isolation. By applying a sandbox to the pod, we get a second security boundary at the pod and can still maintain that network isolation. And the way we are doing this is with technologies like gvisor and Kata containers that bring kind of VM strength isolation and apply it at the pod level. So this isn't increasing container isolation, but it's applying a new sandbox to the pod. What am I doing on time? All right. So let's talk about clusters now. So up until now, we've been talking about things running within the cluster and what is isolated once you already have access within the cluster. At the cluster level, we now have an exterior boundary. So the first thing we add in cluster isolation is this network perimeter. It's now possible to firewall off the cluster in a much more fine-grained way, or even to air-gap the cluster completely in extreme scenarios. We also have a separate control plane. This means it's possible to have completely separate identities and access controls for each cluster. And a separate data store means that a compromise of the cluster will still be limited to the scope of that cluster. So now we have full-on Kubernetes security, totally separate clusters. Are we done? Spoilers, I already said we have one more layer to talk about. So what isn't isolated at the cluster level? Well, at this point, it really depends on your setup. Where are you running your cluster? If you're running in Google Kubernetes Engine, your security model at this point is going to look very different than if you're running on bare metal in your own data center. So the questions you need to ask are, what other resources are exposed on the network? What other services are exposed? If you're running in the cloud, how is access to those services authorized? And do nodes in your cluster, for instance, have access to those cloud services? And so this brings us to the final layer here, the infrastructure layer. And I can't say too much about this because, again, it really depends on where you're running and what your setup is. But it's just kind of comes back to these two questions of understanding what else is exposed on your network. In the data center, do you have other workloads running outside of Kubernetes that might be running in an unauthenticated way that an attacker could exploit from a cluster? And we've actually seen examples of this. So to recap, we started out at the container level talking about some resource isolation that we get and a number of kernel security features that harden that container isolation boundary. At the pod level, we add in network isolation and a little bit more resource isolation. With Kubernetes namespaces, we get stronger control plane isolation. And then at the node level, we finally add in a second security boundary, much stronger resource isolation, and better data isolation as well. With the cluster level, we have stronger network isolation still, separate control planes and separate authorization mechanisms mean better control plane isolation and data access that comes with that. And then finally, at the infrastructure level, this is really as good as it gets. Pause here for a second. So in conclusion, which layer should you design your application for? Which layer should you plan on having isolation at? I'm not suggesting that every workload should be in its own cluster, in its own data center. That would be absurd, very expensive and hard to design, and defeat the purpose of Kubernetes completely. So the answer here is really that actually only you can answer this. Sorry, it's sort of a non-answer. But know your threat model, understand what kinds of data you're trying to protect, who your attackers are, and sort of weigh the trade-offs of the cost of adding in more isolation and the complexity versus the ease of relying more on just the native Kubernetes primitives. So that's what I have for you today. Thank you. Here's a few resources to learn more. And looks like we have a couple minutes for questions. Anyone? Well, if you would like to chat afterwards, I'll be around and would love to answer your questions and talk more about this. Thank you.